Okay, we got a battery being modeled as a seat of EMF in series with a resistor. I'll call it little r, and this will be script E. I'm going to call this point A, point B. What's the terminal voltage of the battery when it's not connected to anything? From the textbook, you know, the terminal voltage is just the ideal seat of EMF, but we can also prove it. To get the voltage across the device, you sum the voltage changes, the potential changes from one point to another. So I'll go from here to here, from A to B, V. A to B is going to be equal to, I'll go minus, plus, there is no current, so I guess I'll put that on there. I is equal to 0, with the current defined as positive in that direction. I have this the high side and that the low side, but it's kind of silly to define it as positive in any direction since it's 0, but still I can say it's script E, just sum the voltage changes from A to B to get the voltage of B with respect to A, or the voltage A to B. So I get plus script E minus I times little r, but this is 0, so I quickly proved that the voltage from A to B is just equal to script E. That's given as 9 volts, so VAB AB equals 9 volts. Should probably put that in here as well. Go blue. Equals 9 volts, and R was equal to 1.20 ohms. Alright, that takes care of part A. Part B, terminal voltage when it's connected across a 52 ohm resistor. I've got the circuit I've got then is seat of EMF, my little tiny resistor, all that's inside the battery, and then outside the battery I got R. So R is equal to 52 ohms, little r is equal to 1.2 ohms, script E is equal to 9 volts. And I'll do Kirchhoff's law with, let's see, this loop right here. I start on this conductor in the lower left-hand corner. I wind up on the conductor in the lower left-hand corner that I'll call loop 1, KVL1, yields, let's get some of these plus and minuses labeled. Plus minus, I'll call the current positive that way. So this becomes plus minus, current into the high side, out the low side, plus minus. And I got, let's see, E, that's a minus E, and then minus I times little r, and then a minus I times big R is equal to 0. And I mislabeled script E, so the short side is the negative, so that's a plus. Alright, then everything's cool. Solve that for I. Script E divided by R plus capital R. So I is 9 volts divided by 1.2 ohms plus 52 ohms. it tells us that I equals 0.16917 volts per ohm, which is amperes. That's I. I don't think that's the answer to the question. Let's. What is the terminal voltage of the battery when it's connected across a 52 ohm resistor? So now I do that same thing. I'll sum from point A to point B, A to B. VAB is the terminal voltage. I guess I need to see that, so I'm going to go over to here. So from here, my solution continues up here. VAB, just sum from here to there, sum the voltage changes, that's equal to plus script E, and then minus I times little r, which is 9 volts minus 0.16917 amps times 1.2 ohms, and I'm getting, let's see, 8.797. 99. I'll call it 8.7970 I wrote down 5 sig figs, 5 digits. Only 3 of them are actually significant, so I'll put the bar over that one. And that's volts. And go ahead and write out the word volts there. So that's my answer for part B. So I just use Kirchhoff's laws. Keep in mind, when we do it around a loop, what we're saying is the voltage between this point and this point is 0. I just sum up all the voltage changes from that point right back to the same point. And that's why I've got the equals 0. If I sum the voltages not around a loop, but just from one point to another, then I'm getting the voltage difference, or the potential difference between the first point and the second point, how much higher the second one is than the first point. And that's what I do to get the terminal voltage, because they want it between 2 points. So instead of saying equals 0, I say equals V A to B, which is, I don't go all the way around the loop, I just sum the voltages from point A to B and get this one. Alright, so very similar to using Kirchhoff's voltage law, except instead of saying I'm getting the voltage change from this point to this same point, which is always going to, and setting that equal to 0, I get the voltage change from point A to point B, and I call it V A to B, VAB. And that is the terminal voltage for the battery, which I expected to be a little bit less than the open circuit terminal voltage, which was 9 volts, which is the voltage across the ideal C to VMF. And that's enough for this video, in which I solved SAC 212 problem number 7.